Noche cósmica.
Imagine yourself suspended in the absolute stillness of deep space, so far from any star that the darkness around you has become almost tactile, almost solid. There is no sound here, not even the memory of sound. Light takes years to cross the distances between objects. The vacuum itself seems to hold its breath. And somewhere in this vast quiet, invisible to any eye, drifting through the blackness in a region of space that looks identical to every other region, there exists a point so strange, so fundamentally alien in its properties, that it bends the very nature of reality around itself. It is a star, though nothing in your intuition would recognize it as such. It is smaller than a city. It is denser than the entire weight of the sun crushed into a sphere the size of a mountain. And wrapped around this tiny, impossible object is a magnetic force so powerful, so utterly incomprehensible, that it would rip the iron from your blood from 1,000 kilometers away. This is a magnetar, and although we have only known of their existence for a handful of decades, these objects represent some of the most profound mysteries in astronomy, while also serving as reminders of just how varied and extreme the cosmos can be. There is something deeply calming about contemplating these dead stars from a safe distance, isn't there? Perhaps it is the very remoteness that soothes us. We are free to wonder without fear. We are free to admire the violent processes that created them without facing any of their consequences. The story of magnetars is a story about stellar death, about the transformation of matter at densities that our minds can barely grasp, about magnetic fields so intense they defy earthly comparison. And yet, when told slowly, when allowed to unfold gently across the landscape of your imagination, it becomes something quite different from a story of violence. It becomes an invitation to look deeper into how our universe works, to understand the hidden architecture beneath the visible light we see each night. If you find yourself drawn to the slow, methodical exploration of such objects, to the idea of drifting through scientific wonder at the pace of a quiet evening, to the notion that cosmic mysteries can be as soothing as they are profound, I would warmly encourage you to subscribe for more of these long-form journeys into the most relaxing facts about magnetars and the deep space phenomena that surround them. Each episode is designed to guide you through authentic, accurate science, while maintaining the gentle rhythm of discovery, the sense of marvel without urgency. We'll explore these objects together, piece by piece, in the weeks and months ahead. For now, let yourself drift a little further into the silence. The story of how we came to know about magnetars is itself a story of patience, of attentive observers watching the sky night after night, and of sudden, brilliant moments of recognition when the pieces finally fell into place. But before we arrive at that moment, before we encounter the gamma-ray flashes that first hinted at these objects' existence, it helps to understand what you are approaching. It helps to have a sense of scale, a foundation upon which to rest the wonder. A magnetar's magnetic field is perhaps the easiest concept to hold on to, even though the numbers attached to it exceed our everyday experience so thoroughly that they almost become poetic. A typical magnet on your refrigerator, the kind that holds a shopping list or a child's drawing, possesses a magnetic field strength of perhaps a few hundred Gauss, a unit of measurement named after the mathematician Carl Friedrich Gauss. Earth's own magnetic field, the one that guides compass needles and protects us from solar wind, measures only about half a Gauss at the surface. A hospital's MRI machine, one of the most powerful magnets humans have ever constructed, creates a field of about 1 to 3 Tesla, which translates to roughly 10,000 to 30,000 Gauss. These are the tools of modern medicine and magnetism. These are the most intense fields we can reliably produce with our best technology. A magnetar produces a field of 100 trillion Gauss. 100 trillion. The number itself seems to dissolve into abstraction. And yet, what does this mean in practical terms? what would it actually feel like? Imagine, if you will, that you possessed a Magnetar's field at a distance of 1,000 kilometers, still incomprehensibly far away, still entirely safe. At that distance, the field would be powerful enough to fatally disrupt the electrical signals in your nervous system. It would erase the magnetic properties of any metal object you carried. It would strip electrons from atoms, ionizing them in a process called diamagnetic levitation. It would, in essence, unmake the ordinary chemistry of matter. And this is at 1,000 kilometers away, in what would seem like the gentlest whisper of the Magnetar's actual power. At the surface of the star itself, the field reaches densities so extreme that the very concept of matter becomes negotiable. The field becomes almost as important as the material itself, and that is what makes magnetars so beautiful to contemplate from afar. They remind us that nature, at its extremes, operates by rules so different from our own that we must almost reinvent our language to describe them. So as you drift deeper into the silence and the starlight, as you allow the picture of this tiny, invisible, monumentally powerful object to settle into your mind, consider what it means that such things exist. Consider that somewhere right now, thousands of light years away, one of these objects is sitting in the darkness, its magnetic field extending outward in all directions, shaping the space around it, occasionally trembling with activity that we, with our patient instruments, can detect from across the galaxy. The Magnetar does not care that we are watching. It does not care that we are trying to understand it. It simply is, as it has been, as it will continue to be for millions of years more, and in that indifference lies a kind of peace. Imagine, if you will, a star so dense that a teaspoon of its material would weigh as much as a mountain on Earth. Now imagine that same star spinning and wrapped in a magnetic field so extraordinarily powerful that it bends the very fabric of space around it. This is what we call a magnetar, and to understand what one truly is, we might begin with something far simpler, far more familiar to you. You have likely held a refrigerator magnet in your hand. It creates a field that you can sense, invisible but present, drawing iron filings into patterns or holding a shopping list against cold metal. The magnetic field around that simple magnet extends outward for perhaps a few centimeters before becoming too weak to notice. A magnetar, by comparison, is a neutron star, the ultra-dense remnant left behind when a massive star reaches the end of its life and collapses inward under its own weight. What makes a magnetar exceptional, what sets it apart from other neutron stars that spin and pulse across the cosmos, is the strength of its magnetic field. It is not just stronger than an ordinary star's field. It is not merely more intense than the magnetic fields we generate in our laboratories on Earth. A magnetar's magnetic field is, in every meaningful sense, catastrophically, almost incomprehensibly powerful. To offer you some shadow of what this means, consider this. If you could somehow place a magnetar's magnetic field around the Earth, it would be so strong that if you held a piece of metal in your hand, the magnetic force trying to rip it away from you would exceed the total weight of all the oceans on our planet. And yet this field is invisible. You would see nothing. You would feel nothing directly. Only the outcome of its presence, the tearing, the pulling, the distortion of everything around it, would make its existence known. A magnetar does not announce itself with thunder or light initially. Its magnetic field simply exists in the darkness, an absolute ruler of the space immediately surrounding it, reshaping particles and energy according to laws that feel almost alien to our everyday experience. The comparison that might serve you best is this. Imagine you have in your home a single spinning magnet, and that magnet is so powerful that if you brought a paperclip anywhere within several kilometers of your house, it would not simply be attracted. The magnetic force would accelerate it to such speeds that it would pierce through your wall, through your body, through anything in its path, all without you hearing a sound. The field works at a distance. It needs no medium. It simply reaches out through empty space and exerts its will. This is closer to what a magnetar does, though even this comparison falls short of the true ferocity of these objects. A magnetar's field is measured in units called Gauss. The strongest magnetic fields we can create in laboratories on Earth reach perhaps a few 100,000 Gauss. The Earth's own magnetic field, the one that guides compass needles and shields us from the solar wind, measures only about half a Gauss at its surface. A typical neutron star might possess a magnetic field of 1,000,000,000,000 Gauss, already almost incomprehensibly large. But a magnetar can hold a field of 100,000,000,000,000 Gauss, or even higher. Some of the most extreme magnetars may reach a 1,000,000,000,000 Gauss, a number so vast that it nearly defies mental visualization. What becomes fascinating as you rest with this image is that such a field does not require the magnetar to be spinning at some impossible speed to maintain itself. This is a common misconception. You might imagine that only the most frantic, fastest spinning objects in the universe could generate such power. But a magnetar's field is not, in the way of ordinary magnets or electromagnets, dependent on motion for its creation. Rather, it is thought to be forged in the catastrophic moments of stellar collapse itself, when the dying star's existing magnetic field is compressed, along with all the star's mass, into a space perhaps only 20 kilometers across. Imagine a magnetic field that once stretched across millions of kilometers, all crushed and concentrated down until it becomes a prison of invisible force around this tiny, infinitely dense sphere. That compression is the source of the magnetar's terrible power. And here is where the magnetar becomes something truly wondrous to contemplate. This field does not remain perfectly stable or dormant. It is alive with activity. The intense magnetic forces can cause fractures in the magnetar's crust, a crust made not of rock or metal, but of neutrons pressed together so tightly that their density boggles the mind. When these fractures occur, they release floods of X-rays and gamma rays into space, violent outbursts that can be detected across countless light years. A single magnetar flare, lasting perhaps only a few seconds, can emit as much energy as our sun has produced in the last 100,000 years. And yet the magnetar continues. It spins, it radiates, it slowly fades, its magnetic field gradually weakening over the eons, until eventually it becomes just another quiet neutron star, no longer worthy of the name magnetar. To hold all of this in your mind, the density, the magnetic fury, the cosmic violence contained in something smaller than a city, is to touch the edge of genuine mystery. Here on Earth, we move through space mostly unaware of magnetism, though it shapes everything around us. But in these distant corners of the universe, magnetism is not a gentle guiding force. It is the dominant architect of reality, the primary shaper of what happens and what is possible. Understanding what a magnetar is means accepting that the universe can be far stranger, far more extreme than our daily experience suggests. If the quiet journey through the cosmos appeals to you, if you find yourself drawn to these slow discoveries about the most extreme and beautiful objects in space, you might consider subscribing to explore more of these unhurried passages into the deep universe, where magnetars and other wonders wait for those patient enough to listen. As we continue deeper into the story of these remarkable objects, it may help to know where they were first discovered and the decades of mystery that surrounded them before science finally understood what these flashes of light truly represented. The first clue that magnetars existed arrived not from purpose-built telescopes aimed at the heavens, but from satellites designed for an altogether different mission. In the early 1970s, during the height of the Cold War, American and Soviet military installations were keeping watch on each other across oceans and continents. Among the instruments stationed high above Earth were gamma-ray detectors, built to monitor nuclear weapons tests and military activity. These satellites, cloaked in their original strategic purpose, were listening to the cosmos without knowing what they might find. Then, on a night in the early decade, something unprecedented appeared. Bursts of gamma rays, the highest energy light known to physics, were flashing across the sky. Not from Earth, not from any anticipated source of radiation, but from somewhere distant in the galaxy. A single burst would arrive, intense and sudden, then fade. Then another would come, sometimes hours or days later. The pattern was unlike anything the instruments had been designed to detect, yet there it was, recorded in the data streams that scientists would later examine with puzzled fascination. What made these bursts so mysterious was their incredible power. In a fraction of a second, one of these events would release as much energy as the sun produces in an entire year. Scientists looked at the numbers, looked at them again, and found themselves genuinely bewildered. Where could such energy come from? What object in space could possibly generate such violence so abruptly, so repeatedly, apparently from the same direction? For a time, there was silence around these observations. The scientific community considered and reconsidered. Some wondered if the satellites themselves might be malfunctioning, or if the data contained instrumental artifacts. Others proposed that these gamma-ray flashes might originate from exotic phenomena, perhaps from the accretion disks around black holes, or from thermonuclear explosions on white dwarf surfaces. These were reasonable guesses given the information available, and yet none of them quite fit. The mystery deepened through the 70s and into the early 80s. What was particularly maddening about these events was their ephemeral nature. A burst would come, be observed, and then it would be months or even years before another one arrived. In an era before global networks could instantly share astronomical data, before the internet made real-time collaboration routine, astronomers searching for these sources faced an immense challenge. By the time they could point their ground-based telescopes toward the location where a burst had occurred, the source had gone silent. No visible counterpart could be found. No radio emission, no infrared glow. The objects responsible seemed to vanish as quickly as they had announced themselves. Yet the detections continued. Vela satellites, built to monitor Soviet nuclear tests, kept recording these strange events. More satellites were launched. More instruments began watching. A slow catalogue accumulated. Astronomers began to recognize a pattern, subtle but real, that certain regions of the sky seemed to produce these bursts with greater frequency. They dubbed these sources soft gamma repeaters because the emissions tended to be in the lower ranges of gamma-ray energy, and because, unlike other known cosmic sources, they would repeat their outbursts. The mystery was tantalizing precisely because it was so incomplete. You had excellent data showing that something real was happening, something energetic and rare, yet no satisfying explanation. Scientists felt they were holding a single puzzle piece, brilliant and geometrically precise, but surrounded by emptiness where the rest of the picture should be. How does one work backward from a burst of radiation to find the object that created it? How does one even know what questions to ask when the phenomenon itself lies outside the boundaries of familiar astrophysics? It would take another decade and a fundamental shift in how astronomers thought about neutron stars before the real nature of these objects would emerge from the fog of speculation. But during those long years of quiet observation, the data accumulated. The mystery remained, patient and distant, waiting for the theoretical framework that would finally make sense of it all. To understand how a magnetar comes to exist at all, we must journey backward through time, far beyond the moment of its discovery, into the story of how a star lives, and eventually, how it dies. And that story begins not with magnetars themselves, but with massive stars, enormous luminous furnaces burning in the darkness, living out their existence on a scale that dwarfs almost everything we know. These are suns that weigh 20, 30, 50 times more than our own sun, burning with such fury that their lives are measured not in billions of years, but in mere millions. A cosmic blink. A star of such magnitude exists in a perpetual state of internal negotiation between two opposing forces, and it is this quiet struggle, played out across eons, that eventually leads to the spectacular collapse we're about to explore together. On one side of this ancient negotiation is gravity, that invisible pull that crushes inward, always inward, drawing every atom of the star toward the center with relentless patience. On the other side, radiating outward from the heart of the star, is the immense pressure and heat generated by nuclear fusion, the merging of hydrogen atoms into helium, a process so violent and energetic that it holds back the crushing weight of all that material pressing down from above. These two forces, gravity and fusion heat, remain in perfect balance for most of a massive star's life. The outward push of light and heat precisely counterweights the inward squeeze of gravity. It is a stalemate, a standoff that allows the star to shine steadily, predictably, for millions upon millions of years. But this balance, however stable it may seem, contains within it the seeds of its own undoing. Because massive stars burn their fuel so incredibly quickly, so wastefully, that eventually, and this is inevitable, that fuel runs out. There comes a moment when the last hydrogen in the core has been fused into helium. When that happens, something subtle shifts. The heat and light production at the center begins to falter, just slightly at first. The outward pressure begins to weaken, and in that moment of weakness, gravity seizes its opportunity. The inward pull, never truly defeated, only restrained, begins to reassert itself. What follows next is not a gentle process. The collapsing core heats up enormously. Temperatures climb so dramatically that helium atoms begin to fuse into carbon and oxygen. Once again, briefly, a new equilibrium is established. The fusion of heavier elements generates enough heat to hold gravity at bay. But this phase too is temporary. These heavier fusions burn even faster, even more wastefully than the hydrogen that came before. Days turn into years, years into centuries, and the chain of fusion continues, each new element fusing into something heavier. Carbon becomes oxygen, oxygen becomes neon, neon becomes magnesium, and so on and so on. The core becomes a kind of layered architecture, a cosmic onion with different elements fusing in different shells, each one burning faster than the last, each one destined to burn out. This process accelerates toward an ending that becomes more rapid, more violent with each passing stage. The timeline of a massive star's final act becomes compressed, almost frantic by comparison to the steady millions of years that came before. Days pass like hours, hours pass like minutes. The star remains largely unchanged from the outside, still shining, still burning, outwardly unchanged, but internally, deep in its core, the architecture is becoming increasingly desperate, increasingly unstable. Layer upon layer of heavier elements accumulates at the center. The core becomes denser and denser, hotter and hotter. And then, inevitably, that core reaches iron. Iron is where the fusion process stops. When the core of a massive star becomes hot enough to fuse silicon into iron, the great chain of stellar alchemy ends. Iron cannot usefully fuse into anything heavier. Or rather, it can, but doing so requires energy rather than releasing it. The chain of self-sustaining nuclear reactions that has held gravity at bay finally breaks. The star has painted itself into a corner, and there is no longer a way out. Gravity, patient and relentless, has finally won. What happens next occurs with breathtaking speed. The iron core, no longer supported by outward pressure, begins to collapse. Not gently, not gradually, but suddenly, catastrophically, in a process that takes not days or hours, but seconds. The core falls inward upon itself with a velocity that increases exponentially, faster and faster. Electrons and protons are crushed together into neutrons. Density increases beyond anything we can easily imagine. Matter becomes so compressed that a teaspoon of this collapsing core material would weigh as much as a mountain on Earth. The density keeps climbing, moment by moment, second by second. And then, at some threshold, something remarkable happens. The neutrons, packed so tightly that they can no longer be compressed further, begin to resist. A fundamental force of nature, the strong nuclear force that binds particles together, suddenly exerts itself with tremendous power. The collapsing core rebounds. It bounces, sending a shockwave tearing outward through the star at nearly the speed of light. This shockwave carries with it an enormous amount of energy that immediately begins blasting away the outer layers of the star in a tremendous explosion. A supernova, the entire outer atmosphere of the star, all that material that was slowly fusing over millions of years, is suddenly ejected into space with such violence that for a few brief moments, this single dying star can outshine entire galaxies of billions of normal stars. And at the center, in the aftermath, what remains? What survives this cataclysm? Only the core, the remnant of that iron nucleus that caused the collapse in the first place. That core has been compressed to such an extraordinary degree that its density rivals that of an atomic nucleus itself. This is a neutron star, a sphere of matter perhaps 20 kilometers across, so dense that a single tablespoon of its material would weigh billions of tons. All the mass of a massive star, perhaps 20 or 30 times the mass of our sun, compressed into a sphere you could hold in your hand if only you could survive the gravitational pull. And it is this neutron star, this remnant born in the death throes of a massive sun, that may, under the right circumstances, with the right magnetic field configuration, become a magnetar. The gravitational collapse that forges a neutron star is the foundation upon which all that follows is built. The violent death of massive stars scattered throughout the galaxy are the birthplaces, the crucibles in which these most extreme objects come to exist. And so we see that to understand magnetars, we must first understand this cascade of stellar death, the struggle of two forces, gravity and fusion heat, a struggle that ends not in quiet, but in supernova fire. Now, if we are to understand magnetars truly, we must first step back and consider the broader family to which they belong. For a magnetar is not simply a neutron star with extra properties tacked on like ornaments. Rather, it exists within a delicate spectrum of stellar remnants, each one occupying its own corner of the universe, each one spinning and pulsing and radiating in ways that tell us something different about the nature of matter itself. Picture, if you will, a lighthouse on a rocky shore. A traditional lighthouse sends its beam out in a steady, rotating circle. It is predictable. It is precise. This is, in essence, what we call an ordinary neutron star, a compact remnant, yes, composed of matter so densely packed that a single teaspoon would weigh as much as all the cars on Earth combined, but one that spins and emits radiation in a relatively orderly fashion. Its magnetic field, while immense by our standards, is still measured in familiar numerical language, billions upon billions of times stronger than Earth's own magnetic field. The radiation it produces follows patterns we can predict. We know where to look. We know when to listen. But now, imagine that lighthouse beginning to pulse, its light growing stronger with each revolution. This is where pulsars enter our understanding. A pulsar is, fundamentally, a neutron star that has been endowed with a particular gift, a spin, often extraordinarily rapid, that creates a beam of radiation focused like a searchlight in a narrowing cone. As the pulsar spins, this beam sweeps across space, and when it points toward Earth, we receive a brief, brilliant flash, then darkness, then the flash again. The timing is so precise, so mathematical and unchanging, that the first pulsars discovered were actually thought to be signals from extraterrestrial intelligence. They possess magnetic fields similar to ordinary neutron stars, but the way they interact with their spinning, the way they focus their energy, creates this distinctive pulsing behavior that makes them such perfect cosmic clocks. And then there are magnetars. Here we venture into something altogether more extreme, more dramatic, though in a way that whispers rather than shouts. A magnetar is, at its heart, a neutron star, just as all pulsars are neutron stars, but one that carries within itself a magnetic field of such colossal strength that it occupies a category entirely its own. Whereas an ordinary neutron star might possess a magnetic field of around 1,000,000,000,000 Gauss, a magnetar wraps itself in a field 1,000 times stronger still, sometimes 10,000 times stronger. To offer a sense of scale, if a magnetar's magnetic field existed on Earth, it would be powerful enough to extract the iron from the blood cells in your body from several hundred kilometers away. It would scramble the electrons in atoms themselves, twisting the very geometry of matter. But how can we hold this concept steady in our minds? Perhaps it helps to think of it this way. Imagine a person at rest. This is your ordinary neutron star, magnetic but relatively quiet. Now imagine that same person beginning to spin, faster and faster, their arms extended, creating a focus of energy and attention. This is your pulsar, the spinning lighthouse. But a magnetar is something different still. It is as though that person were wrapped in an enormous invisible force field of such intensity that their very presence distorts everything nearby. The spinning matters, yes, but it is secondary to the overwhelming presence of that magnetic envelope. A magnetar can spin slowly, even by neutron star standards, and yet its magnetic field will dominate its behavior and its visibility across the cosmos. What fascinates us, when we pause to consider this, is that magnetars appear to be relatively rare among neutron stars. We have catalogued only a few dozen confirmed magnetars in our galaxy and its neighbors, whereas pulsars number in the thousands. This scarcity adds to their mystery. Are they born differently? Do they result from particular combinations of stellar mass and rotation and magnetic inheritance from their progenitor stars? Do some pulsars, over time, evolve into magnetars, or vice versa? These remain open questions, gentle puzzles that astronomers continue to turn over in their minds. What ties them all together? The ordinary neutron stars, the pulsars, and the magnetars, is that they are, each and every one, the surviving cores of massive stars that once hung in the night sky, burning their fuel, illuminating planets and moons that may have orbited around them. The difference lies not in their essential nature, but in the intensity of their magnetic fields and the manner in which they spin, the particular configuration of forces that emerged from each unique stellar death. And in understanding these differences, we begin to glimpse the true diversity of the universe, the countless variations on the theme of stellar collapse, each one creating remnants with their own character, their own way of singing into the darkness. Now, here exists something that may be the most difficult number to hold in the human mind, the true magnetic strength of a magnetar. Picture, if you will, the most powerful magnet you have ever encountered in a laboratory or a doctor's office. A magnetic resonance imaging machine, the kind that hums and whirs while peering into the body's secret spaces, generates a field of perhaps 1.5 to 3 Tesla. That is already a force so concentrated that metal objects become dangerous projectiles, that the human body would experience something approaching invisible pressure. And yet a magnetar's magnetic field, reaches not thousands or millions of times stronger, but trillions upon trillions of times more intense. The numbers themselves become almost poetic in their impossibility. 10 to the 15th Gauss, or some magnetars even reaching 10 to the 16th. Does the mind grasp such enormity, or does it simply drift past like a number glimpsed on a distant highway sign? What becomes more useful, perhaps, is to translate this into sensation. Imagine, for a moment, that you could stand at the edge of a magnetar's field, not close enough to be destroyed, but at some safe distance where the force could still be felt. The pull would not simply tug at your iron-rich blood as a regular magnet does. It would stretch the very atoms themselves. It would align every electron's spin, every nucleus's orientation, into perfect obedience. The human body, that delicate arrangement of molecules held together by electromagnetic bonds, would experience not pain exactly, but a kind of profound reorganization at the atomic level. Every cell would know, somehow, that it stood in the presence of something utterly alien to ordinary matter's experience. The Gauss itself, that unit of magnetic measurement, carries a name from Carl Friedrich Gauss, the 19th century mathematician who helped us understand magnetism's geometry. When we speak of a magnetar field in the trillions of Gauss, we are truly speaking of a force so singular in nature that neutron stars without magnetar strength, ordinary neutron stars with merely 1,000,000,000,000 or 100,000,000,000,000 Gauss, seem almost sleepy by comparison. The difference between 10 to the 12th Gauss and 10 to the 15th Gauss is the difference between comprehensible stellar violence and something that bends the rules of how matter can behave. What happens then when such a field coils around a neutron star? The magnetic field lines themselves become rigid, almost like invisible iron rods, extending outward into space, twisted and braided by the star's slow rotation. These are not gentle field lines, the kind you might trace with iron filings in a schoolroom experiment. These are structures of unimaginable power, capable of storing vast amounts of energy, energy that can, when the crust fractures just so, be released in a burst of radiation that travels across light years as if it were nothing. The magnetic field becomes, in essence, the star's stored memory of its own violent birth, a prison and a battery all at once. One of the most graceful ways to understand this is to consider the concept of the magnetic dipole moment, which describes the overall strength and orientation of a magnet's field. A magnetar's dipole moment is so enormous that if you placed it at Earth's center, its magnetic influence would extend beyond the orbit of Neptune, its field lines threading through the solar system like invisible thread through dark fabric. Yet all of this exists concentrated around an object no larger than a city, spinning in the void, indifferent to the immensity it contains. There is something almost paradoxical about these numbers. The stronger a magnetic field becomes, the more it resists our intuition, the more it slips away from everyday understanding. We know what a magnet is because we have played with them, felt their gentle pull and repulsion. But the magnetic field of a magnetar exists in a realm so far beyond that experience that it becomes, in a way, spiritual rather than physical. It is pure force, pure geometry, pure order, imposed upon the chaos that would normally govern such a small, dense object. And this is where the astonishment settles, in that quiet moment when you consider that this field, this 1,000,000,000,000 times stronger than anything on Earth field, is real. It is not theoretical or imagined. It surrounds actual objects that move through actual space, that emit actual light we can detect with our instruments. It is as real as the ground beneath you, and yet infinitely more foreign to experience. The magnetar asks us to expand what we mean by real, to include in our understanding of the universe forces that our senses were never designed to encounter. For decades, magnetars remained a quiet hypothesis, a mathematical possibility that existed in journals and on chalkboards, compelling but unproven. The theory sat in the minds of patient astronomers, waiting. And then, in 1998, something extraordinary and yet entirely comprehensible happened, observed not from a single observatory, but from satellites positioned across the solar system, each one recording the same distant tremor at nearly the same moment. It was as though the universe had decided to whisper its confirmation on a night when many telescopes were listening. On August 27th of that year, a soft gamma repeater catalogued as SGR 180620 began to stir. Deep within the constellation Sagittarius, approximately 50,000 light-years away, this object, barely wider than a city, yet denser than anything the mind can hold, entered a state of outburst. Now, the word outburst might conjure images of violent explosions, but what happened was something more subtle and deeply strange. The star's crust, that crystalline shell of compressed matter, fractured. Think of it not as a violent rupture, but as a slow, inevitable settling, the way a foundation shifts when the weight above it becomes unbearable, the way ancient ice cracks under its own accumulation. This fracture released energy stored in the Magnetar's colossal magnetic field, and that energy began to radiate outward in cascades of X-rays and gamma rays. The telescopes that had been waiting, some of them in orbit, some of them on the ground, suddenly lit up with simultaneous detections. There was a kind of quiet vindication in that moment, a confirmation arriving not with fanfare, but with clear, measurable data. The Magnetar theory, which had seemed so speculative, so elegantly theoretical, suddenly possessed observational teeth. What makes this 1998 outburst particularly significant is not merely that it confirmed magnetars exist, but that it demonstrated something about their behavior that matched predictions so closely. The pattern of emission, the frequency and intensity of the gamma-ray pulses, the way the energy faded over days and weeks, all of it aligned with what calculations had suggested ought to happen if such an object underwent a crustal fracture. It was as if the universe had quietly agreed with the mathematics, answering an old question that had hung in the air. Imagine observing a distant lightning storm from a place of complete safety, where you can see the brightness flash across the darkness but feel no threat, hear no thunder. That is something like what astronomers experienced when SGR 1806-20 erupted. The event was cataclysmic in its local context. The energy released in that single outburst, had it occurred near Earth, would have fundamentally altered our planet's magnetic environment and potentially rendered satellites and power grids inoperable. Yet from 50,000 light-years away, it appeared as an exquisite pattern of radiation, a demonstration of physics under extreme conditions, beautiful precisely because it was safely distant. The outburst came in waves, a phenomenon that speaks to the internal architecture of the magnetar. The initial flash, sometimes called the giant flare, was remarkably bright and brief. But then, in the hours and days that followed, the object continued to emit repeating pulses, softer echoes of that initial rupture. These repetitions were not random fluctuations, but seemed to follow underlying patterns, as if the magnetar's crust was settling into a new configuration, releasing stored elastic energy in measured increments. Each pulse carried information about the density of material within the star, about the temperature, about the structure of the magnetic field itself. For magnetar theorists, this sequence of emissions was like reading a carefully written letter. Every detail spoke volumes. The fact that the pulses showed quasi-periodic oscillations, recurring rhythms rather than pure chaos, suggested that the crust had fractured in a way that allowed resonant motion, standing waves in the ultra-dense material that vibrated like an instrument tuned to frequencies imperceptible to human ears, but perfectly legible to sensitive detectors in space. What quiets the mind about this event is how orderly it was. The universe did not need to cooperate with theoretical models, yet SGR 1806-20 in 1998 seemed to cooperate beautifully. The mathematics held. The observations arrived exactly where physicists had placed their calculations. There is something deeply soothing about that kind of alignment between theory and reality. The sense that human understanding, modest as it is, can still grasp genuine patterns in the cosmos. And beyond the immediate confirmation lay another layer of satisfaction. This outburst, and others that followed from different magnetars, allowed astronomers to begin mapping the interior of these objects without ever traveling to them, without ever reaching across the stars. Through the signatures of oscillation, through the decay rates of emission, through subtle details in the timing of pulses, a three-dimensional portrait could be sketched, a picture of what exists inside matter, compressed to densities our intuition cannot fathom. It was detective work, conducted at light speed and across light years, a slow unraveling of secrets that the Magnetar had revealed in that August night, a message from the extreme end of stellar death, carried safely to listening ears. Now, there is something deeply calming about thinking of a Magnetar not as an engine of chaos, but as a world unto itself. A frozen world, yes, but a world with a geography all its own, a surface, a crust, a slow, grinding interior that shifts and settles, and sometimes, in its own patient way, breaks. We think of earthquakes on Earth as violent, sudden ruptures born from the grinding of vast tectonic plates, but on a Magnetar, the phenomenon takes on an altogether different character when you begin to understand what is happening at the atomic level. Picture a crust, if you will, a crust made not of rock and silicate minerals, but of matter so densely compressed that a teaspoon of it would weigh as much as a mountain. A crust perhaps a kilometer thick, surrounding a core of unimaginable density beneath. This crust is not inert. It is under profound stress. The magnetic field lines that suffuse every atom, every nucleus within, they press and push with forces so enormous that the very structure of matter itself bends to accommodate them. The electrons, the protons, the neutrons, all are squeezed and oriented by fields 1,000,000,000,000 times stronger than anything we can conjure in our laboratories. This creates what we might call a kind of cosmic brittleness. The crust becomes rigid, locked, waiting. And then, as time passes, months or years, or perhaps even longer, the internal structure of the Magnetar continues to evolve. The core is slowly cooling, radiating away its ancient heat. The magnetic field itself is shifting, reconnecting, redistributing its energy through the star's interior. Stresses accumulate, the crust resists, until, without warning, something gives way. When a starquake occurs on a Magnetar, the crust suddenly shifts. A fraction of a centimeter, perhaps. A rupture that propagates through the crystalline lattice at the speed of sound through neutron-degenerate matter. The release is not gradual. It is sudden, and in that sudden release, something remarkable happens. The magnetic field lines, which had been pinned in place by the rigid structure of the crust, suddenly snap free. They reconnect, they reconfigure, and in reconfiguring, they dump enormous amounts of magnetic energy into the surrounding plasma. Think of it this way, if it helps to settle your mind into the metaphor. Imagine a frozen lake in winter. The surface is rigid, locked in place by cold. Beneath it, currents flow, pressures build. A crack suddenly forms, runs across the ice with a sharp report. Where the crack opens, water wells up from below and refreezes, changing the shape of the surface slightly. Something shifts. The whole geometry is altered, subtly, and the surface remembers it. A Magnetar's starquakes are similar in their essential anatomy, though the forces at work are incomprehensibly greater and the consequences far more energetic. We believe, though observations are still gathering evidence, that a starquake is a moment when the magnetar's crust actually breaks, when strain that has accumulated over years or decades suddenly exceeds the structural strength of matter under these extreme conditions. The break allows the magnetic field to reconfigure, to settle into a slightly lower energy state. But the transition itself releases radiation. It produces those gamma-ray flares that we detect across light years of space. What makes this genuinely soothing to contemplate is the sense of geological inevitability to it all. Starquakes are not random violence. They are part of a slow, rhythmic process, a magnetar building stress, releasing it, settling, building again, like the breathing of some ancient, crystalline world, like the slow creep of continents on Earth across millions of years, except compressed into moments, separated by months or years rather than millennia. And here is something that perhaps deserves quiet reflection. We do not yet fully understand what determines when a starquake will occur. There are models, certainly, simulations that suggest stress accumulation should reach a breaking point after certain timescales. But observationally, magnetars can be silent for years, and then suddenly, following some internal threshold we cannot yet predict, they rupture. The starquake comes, the magnetic field reorganizes, and the magnetar settles once more into its vigil. There is also the intriguing possibility that the crust itself changes after each quake. The breaking and reforming of the crystalline lattice at the surface might gradually alter the star's moment of inertia, its resistance to rotation, and indeed, astronomers have observed subtle changes in rotation rates following large outbursts. The magnetar is literally changing shape, physically restructuring itself with each violent release of pent energy. When you lie in darkness thinking about this, there is something almost peaceful in acknowledging that even the most extreme objects in the universe follow these deep, slow rhythms. Stress and release, accumulation and rupture. A magnetar does not exist in a state of constant explosion. Most of the time it is simply waiting, cooling, settling, the crust slowly reorganizing itself, atom by atom, in the grip of forces we can barely comprehend. And every so often, when the strain becomes too great, it breaks. The whole star convulses gently, the magnetic field breathes, and then the waiting resumes. In this way, a magnetar is not so different from the Earth beneath you. Both have crusts, both experience earthquakes, both release energy in sudden, dramatic ways. The scale differs by factors that are almost impossible to fathom, but the principle is the same. The principle is geology. The principle is patience. The principle is the slow, inevitable rearrangement of matter in response to forces that never truly stop working, never truly stop pressing. What happens in those moments when a magnetar suddenly releases its energy into the cosmos? The answer unfolds in layers of physics so intricate that even describing it feels like watching light bend through an invisible prism. A magnetar's surface, you might imagine, is never truly still. Beneath that thin crystalline crust, the magnetic field churns with tremendous tension, threading through the star's interior like invisible rope under impossible strain. And every so often, that tension breaks. When it does, the release is not gradual or gentle. It is violent in the way that only stellar physics can be violent, sudden, absolute, and broadcast across billions of light years. The mechanism begins with what we call a starquake, which we explored before, but now consider what happens immediately after that crust fractures. The sudden shift in the star's architecture causes the magnetic field lines themselves to reorganize. They snap, like rubber bands released from a twisted knot. In that instant of reconfiguration, electrons and charged particles that live in the magnetar's atmosphere are accelerated to nearly the speed of light. The friction and collision of these particles, moving with such fury through that monstrous magnetic field, creates X-rays and gamma rays, the most energetic light the universe can produce. Think of it as a kind of stellar respiration, though that image only reaches so far. When you breathe, air flows into your lungs and oxygen enters your blood. Here, magnetic energy converts into electromagnetic radiation. The star is not alive, of course, but there is something almost organic in the rhythm of these releases. Tension building, fracture occurring, light escaping. The magnetar does not choose when to breathe out. The physics chooses for it. The X-rays come first, often in a bright initial flash. They pour outward from the magnetar's surface in all directions, racing through the vacuum at light speed. Within seconds, gamma rays follow, arriving at observatories across the solar system where sensitive detectors catch their arrival. These are the highest energy photons, carrying information about conditions so extreme that recreating them on Earth remains impossible. A single gamma ray from a magnetar contains more energy than any gamma ray produced by the Sun over an entire year. What makes this process particularly elegant, from a physicist's perspective, is that the magnetar does not need to rotate to produce these bursts. An ordinary pulsar sends out beams of radiation like a lighthouse because the star spins and its magnetic pole points sometimes toward us, sometimes away. A magnetar, by contrast, releases its radiation through the violent relaxation of magnetic stress, regardless of its rotation. The star could be spinning slowly or quickly, and still these bursts can occur. The magnetic field itself becomes the engine of the explosion. The intensity varies depending on the region of the magnetar that fractures. If the quake occurs near the magnetic poles, where the field is strongest, the outburst tends to be more violent. If it happens near the equator, the same restructuring produces something gentler. We might say a magnetar's outburst depends on where it breaks, much as a crack in different materials leads to different sounds, different shapes of failure. The energy released in a single large magnetar burst is staggering in ways that numbers struggle to convey. Imagine the total energy the Sun will emit over the course of the next 1,000 years. Imagine that enormous figure. A magnetar, in the span of perhaps 1/10 of a second, can release as much energy as that. And then it is silent again, at least for hours or days or years. The energy goes outward, spreads through the darkness, and distant detectors register a brief, brilliant signature. What happens to that light as it travels? The X-rays and gamma rays do not sustain themselves indefinitely. They cannot pass through ordinary matter without being absorbed or scattered. The magnetar's own atmosphere, mostly composed of exotic matter at incomprehensible densities, absorbs some of them. Others escape into the surrounding nebula, the remnants of the original supernova that left the magnetar behind. As they move through this diffuse material, they ionize atoms, strip away electrons, heat gas to millions of degrees. The bursts ferve invisible paths through space, momentary disturbances in an otherwise patient cosmos. Some of the radiation that escapes the immediate vicinity travels unfettered toward us. It is a remarkable thing to consider. Light that began as the structural failure of a dead star, squeezed into a space no larger than a city, travels across light years of void and enters our instruments. We detect it. We measure its properties. We ask what it can tell us about the magnetar that sent it. The frequency at which these bursts occur varies dramatically from one magnetar to another. Some release energy constantly in small, frequent tremors, bursts every few hours, as if the star is breathing in a shallow, anxious rhythm. Others might rest for weeks or months, then suddenly unleash a cascade of activity before returning to silence. The longest known magnetar outburst lasted for months, a sustained period of elevated radiation emission as if the star struggled to reach a new equilibrium. Others discharge in sharp single blasts, brief and brilliant. Can we predict when a burst will occur? Not yet. Despite enormous advances in our understanding, magnetars retain their unpredictability. This is one of the enduring mysteries, and perhaps it is fitting that these strange stars should keep their secrets. The universe does not feel obligated to conform to our desire for order and foreknowledge. As the energy propagates outward, carried by those tireless photons, it carries information encoded in its spectrum, its timing, its intensity. Future observers, studying magnetar bursts centuries from now, might decode messages in that radiation that we cannot yet read. The light breathes across the galaxy, and in that breathing, it speaks of physics in its most extreme and unforgiving form. Among the catalogued magnetars known to astronomers, a few have earned a kind of historical prominence, not through fame, but through the sheer audacity of their outbursts, and the way those outbursts have reshaped our understanding of what the universe is capable of producing. One such object carries the designation SGR 1180620, and its story is one of patience, precision, and a moment of cosmic violence so sudden it rewrote the expectations of an entire field. Soft gamma repeater, a name that carries within it the quiet hint of what these objects do. They emit bursts of soft gamma rays, and they repeat, though not on any schedule that human intuition finds comfortable. SGR 10620 was first catalogued after scientists began noticing bursts from that region of space in the 1970s, though it would take decades before the connection between these repeating flashes and magnetars became clear. For years, this source remained something of a puzzle, a whisper in the data that astronomers noted and filed away, a gentle mystery that demanded explanation. The life of this magnetar would remain relatively quiet, in the way that a magnetar's quiet is still extraordinarily powerful, until December of 2004. On the 27th of that month, at a moment that seemed ordinary to the rest of the galaxy, SGR 180620 produced what scientists would later call a giant flare, a release of energy so immense that for a brief moment, this distant magnetar outshone the brightest gamma-ray sources in the cosmos. The burst lasted only about 1/10 of a second, a duration so brief that it might seem insignificant, and yet within that fraction of time, more energy was released than our sun will produce in roughly 1,000,000 years. To sit with that fact for a moment is to encounter one of the universe's most profound contrasts. Somewhere far across the galaxy, hidden within dust and distance, a sphere of matter perhaps 20 kilometers wide and more massive than the sun itself, simply convulsed. The magnetic field that had been wound so tightly around it for thousands of years found release in that single catastrophic instant. The light from that flare traveled through space for centuries before reaching Earth's instruments, where it registered as a brightness that startled astronomers and prompted urgent international coordination to observe every photon of information that followed. What made this flare particularly remarkable was not merely its brightness, but the way it allowed scientists to witness what happens in the aftermath of a magnetar's sudden reconfiguration. The initial burst was followed by a series of oscillations, a kind of ringing that persisted for several minutes. Imagine a bell struck with incomprehensible force, but a bell made of neutron star material at nuclear density, still vibrating in ways that sent ripples of light across space. These oscillations encoded within them information about the internal structure of the magnetar itself, the density of material at different depths, the way that a crust of iron and nickel might behave when the magnetic field beneath it undergoes a sudden violent shift. Another magnetar that has become well known through its outbursts is SGR 162727-2041, which produced a notable outburst in 1998 that helped cement the magnetar hypothesis at a time when some skepticism still lingered among astronomers. This source too has given researchers windows into the behavior of these extreme objects, allowing careful observation of how a magnetar's X-ray brightness can evolve over weeks and months following a major flare, how the light output decays according to patterns that theoretical physicists can now model and predict with increasing success. The naming and cataloguing of magnetars may seem like a technical matter, a simple matter of coordinate systems and catalogue numbers. Yet there is something quietly profound in the fact that astronomers around the world can now sit down together and speak, without ambiguity, about SGR 190529, or any of the dozens of magnetars now listed in the scientific literature. Each designation marks a distant object that has been observed, measured, and added to humanity's map of the cosmos. Each one has, at some point, done something remarkable enough that its light reached Earth and was captured by sensitive instruments designed precisely for this purpose. There exists something meditative in contemplating this catalogue of magnetars as a kind of slow, ongoing discovery. New magnetars continue to be discovered, often when they awaken from apparent dormancy with a sudden burst of activity. A source might be quiet for years, sending out only faint emissions that barely register above background noise. And then one evening, or one morning, depending on where the Earth happened to be in its rotation, astronomers notice it has brightened considerably. They check their records, confirm that this object was indeed known before, perhaps with a longer history than the instrument's operators themselves realized, and they add new observations to a growing archive that spans years and decades of careful watching. The pattern that emerges from studying multiple magnetars, from examining the statistics of their flares and the characteristics of their outbursts, is one of individuality within similarity. Like snowflakes or fingerprints, each magnetar seems to have its own particular behavior, its own preferred range of brightness, its own quirks and preferences for how it releases the enormous energies stored within its magnetic field. Some magnetars seem to produce giant flares frequently, or frequently in the context of cosmic time, perhaps once per decade or century. Others may harbor the potential for such flares, but reveal little activity for human lifespans stretched across decades of observation. In this way, the catalogue becomes not merely a list, but a kind of natural history, a collection of individual portraits of objects that have proven themselves far more diverse and complex than early theories anticipated. Now, if we were somehow able to drift beneath the surface of a magnetar, past that devastatingly dense crust, we would encounter something that challenges our earthly intuitions about what matter can be. The interior of a magnetar is not solid in any way we have ever touched or held. It exists in states that belong almost entirely to the realm of theory and careful mathematical inference, because no laboratory on Earth could ever recreate these pressures, these temperatures, these impossible conditions. Yet astronomers and physicists have spent decades describing what they believe unfolds within. The outer shell of a magnetar, what we call its crust, is extraordinarily thin compared to its radius, much like the skin of an apple compared to its flesh. This crust is thought to be composed of nuclei so densely packed that a teaspoon of this material would weigh as much as a mountain. The nuclei are arranged in a crystalline lattice, almost like a vast cosmic mineral. Picture, if you will, a perfect geometric structure of matter, frozen at temperatures that would liquefy any element on Earth, held together by forces so immense that they keep every atom locked in place. The crust itself may be only a few hundred meters thick, yet it bears the weight of all the layers below. Is it any wonder that when that weight shifts, when the magnetic field threading through these crystals reorganizes itself, the entire structure can fracture and tremble? Beneath this crystalline shell lies a region thought to be composed of neutrons arranged in a kind of nuclear pasta. This is not a poetic exaggeration. Physicists actually use this term because the structures formed by the neutrons take on shapes that resemble spaghetti, lasagna, and gnocchi, twisted and layered in ways that depend on the precise conditions at each depth. These shapes emerge from a balance between the strong nuclear force trying to bind neutrons together and the electromagnetic repulsion working to keep them apart. The visual strangeness of these arrangements belies their physical elegance. They are solutions to equations of motion, frozen in form by unimaginable pressure. But the true heart of the magnetar, the region that occupies most of its mass despite its compact size, is thought to be a realm of something called neutron superfluid. This is one of the most remarkable substances that quantum mechanics allows to exist. A superfluid is a state of matter so cold, so quiet, so intrinsically orderly that it flows without any friction whatsoever. When a superfluid moves, it does not dissipate its energy through collision and heating, as normal fluids do. Instead, it moves with a kind of eternal persistence. Imagine pouring a liquid into a bowl, and having that liquid flow and slosh not just for a moment, but for millions of years, never slowing, never losing energy to warmth. This is what a neutron superfluid does, theorized to exist in the core of a magnetar. Within this superfluid ocean, scientists believe, the neutrons are organized into pairs. These pairs are bound together by the strong nuclear force in a way that creates a coherent quantum state. The pairing is not unlike the pairing of electrons in a superconductor here on Earth, where electrons form pairs and move through a material with zero resistance. When we detect vortices in laboratory superconductors, small whirlpools of quantum circulation, we are seeing a tiny echo of what might be happening at the core of a magnetar. The magnetic field itself is thought to be pinned to these vortices, thousands of them threading through the superfluid like strands through silk. And this is how the magnetar's field remains so stable, so extraordinary, pinned in place by quantum order. How does this internal architecture work as a unified whole? The magnetic field does not float freely in some abstract space. It is woven into the structure of the magnetar itself. The field is anchored to the crustal lattice above, and it is threaded through the superfluid core below. When the crust fractures, when the geometry of its crystalline structure shifts, the field itself must shift with it. This is what gives rise to the giant flares we have observed, the sudden violent releases of energy that can brighten for a few seconds and rival the light of the entire galaxy around the magnetar. The field releases energy not as an explosion in the human sense, but as a cascade of magnetic reorganization, a reshuffling of the invisible architecture that holds the magnetar's form. The distinction between the crust and the core, between the solid and the superfluid, is not a sharp boundary, but likely a gradual transition. At intermediate depths, protons and electrons might exist in a state that is neither fully solid nor fully liquid. Superconducting proton states have been proposed to exist within this region. The protons, moving through the lattice without resistance, would carry electric currents that reinforce the magnetic field. The distinction between matter and magnetism blurs in such conditions. They are not separate things here, but rather different aspects of the same phenomenon, the same quantum dance of particles and forces. What is perhaps most calming to consider, in a strange way, is that all of this, the crystalline lattice, the nuclear pasta, the superfluid core, the threaded magnetic vortices, all of it is utterly inaccessible to us, and yet comprehensible through mathematics. We do not need to touch this architecture to understand its principles. Decades of study have allowed physicists to work out the equations that govern how matter behaves under such extreme conditions. The magnetar becomes, in this sense, a kind of vast natural laboratory where the universe itself performs experiments that no human could ever conduct. And yet we can learn from these experiments simply by receiving the light and radiation they broadcast across the void. Within a magnetar, then, there exists what might be called a kind of eternal architecture. The crustal lattice has held its structure for millions of years, stable despite all that pressure and magnetism, crystalline and geometric. The superfluid below flows endlessly, its energy preserved, its motion perpetual. The magnetic field threads through it all, pinned and waiting. And in that architecture rests a kind of quietness, an order so complete that it transforms the unimaginable into something almost serene. For many years, astronomers observed something that seemed to belong to an entirely different corner of the cosmos. Fast radio bursts, sudden, brilliant flashes of radio energy that arrive from distant galaxies, lasting only milliseconds before vanishing completely, appeared to be distinct from magnetars in almost every way. They were quick, they were far away, they seemed to originate from galaxies billions of light-years distant, while the magnetars we had catalogued were our closer neighbors, relatively speaking, within our own galactic neighborhood. The two phenomena seemed to inhabit separate worlds of astrophysics, belonging to different classification schemes, different detection methods, different stories altogether. And yet, as the years passed and astronomers accumulated more observations of fast radio bursts, a quiet whisper began moving through the scientific community. What if some of these bursts, rather than coming from some distant, yet unnamed object we had not yet discovered, were actually the signature of magnetars? What if the violent magnetic tempest that could tear a magnetar's crust apart could also produce radio emissions bright enough to be detected halfway across the observable universe? It was a soft, speculative thought at first, more of a wondering than a certainty, but it began to reshape how some researchers approached the mystery. The appeal of this connection lies partly in magnetars' sheer power and partly in their strangeness. A starquake on a magnetar's surface releases an amount of energy that seems almost impossible to describe in human terms. Energy comparable to all the electromagnetic radiation our sun has released throughout its entire existence, compressed into a single second or two. When such a cataclysm occurs, when the crust fractures and the magnetic field reshapes itself, the rippling disturbances could theoretically produce radio waves of extraordinary brightness. If a magnetar flare were to point its beam toward Earth at just the right moment, with the geometry of its magnetic field aligned properly, could we not detect it as a brief, brilliant flash of radio light? Could we not mistake it, initially, for something coming from an entirely distant source? Several fast radio bursts have shown properties that make this explanation tantalizing. Some repeat their signals, coming back to the same location in the sky multiple times, sometimes in patterns that seem almost rhythmic. Ordinary neutron stars and pulsars repeat, of course, it is their nature, but fast radio bursts were initially thought to be one-time events, singular fireworks. The discovery of repeating fast radio bursts changed that assumption, and among the repeating bursts, some appear to originate from locations that could harbor magnetars. Some seem to come from star-forming regions where young, massive stars might collapse into magnetars. The alignment between what we know about magnetars and what some fast radio bursts seem to require has caught the attention of careful observers. Yet the connection remains unproven, and therein lies the gentleness of this open question. No fast radio burst has been conclusively shown to come from a known magnetar. No magnetar has yet been caught producing a fast radio burst bright enough for us to detect. It remains a beautiful hypothesis waiting for confirmation, a puzzle where some of the pieces seem to fit, but not all of them, not yet. The distances involved create one barrier. The magnetars we can observe in detail are relatively nearby, while most fast radio bursts seem to come from very distant galaxies, making simultaneous observations of both phenomena difficult to achieve, and the physics, while suggestive, is not yet fully worked out. Could a magnetar's magnetic field geometry really channel its energy into a tight beam of radio waves? Would the energetics balance correctly? These are the kinds of questions that keep astrophysicists awake, pondering the small details that might unlock a larger truth. There is something peaceful about sitting with an open question like this, rather than rushing towards certainty. It reflects the actual nature of scientific discovery, which moves not in sudden revelations, but in gradual accumulation, in patient observation, in the slow building of evidence that eventually points toward truth. New telescopes are being built, new surveys are being conducted, and the catalogue of fast radio bursts grows with each passing season. Each new observation adds a thread to the tapestry. Some threads strengthen the connection to magnetars. Others suggest alternative explanations, different sources, different phenomena entirely. The mystery deepens even as understanding slowly grows. What becomes clear in contemplating this possibility is how much of the universe's most violent, most energetic phenomena may be connected through magnetism. A magnetar is, fundamentally, a device for converting magnetic energy into motion and light and heat. A fast radio burst is a burst of electromagnetic radiation traveling across the cosmos. Both involve the transformation of one form of energy into another. Both are brief, intense, and difficult to predict. If they are connected, it would suggest that magnetars play an even more important role in shaping the universe's appearance than we previously understood. That these bizarre remnants of dead stars send their signatures not just across our galaxy, but to the farthest reaches that our telescopes can see. Whether that connection will ultimately prove true remains for future observers to discover. One careful measurement at a time, in the quiet depths of night observatories, where telescopes keep their patient watch over the distant, inexplicable sky. Among the billions of neutron stars scattered throughout the galaxy, magnetars occupy a peculiar and vanishingly rare corner of that stellar graveyard. If you were to gather every known magnetar in our Milky Way, the count would number somewhere around 20 or 30 confirmed cases, perhaps a few dozen more hiding in the infrared dust where telescopes have only begun to look. In a galaxy that holds 200 billion stars, this makes magnetars the kindest of cosmic rarities, objects so precious in their isolation that each one discovered feels like finding a particular stone on a particular beach at midnight. Yet here is what makes this rarity even more poignant. Magnetars do not burn forever. They are not eternal. The very magnetic fields that make them so extraordinary, so energetic and so alive with invisible force, are fields that gradually, inexorably, dissipate over timescales of tens of thousands of years. Imagine a length of time stretching back to the last ice age, to the first settlements of human beings in what would become our civilizations. The magnetic fields of magnetars slowly fade. The tremendous reserves of magnetic energy that once erupted in violent flares and lit up distant regions of space begin their long, patient descent toward silence. A young magnetar, born perhaps in the catastrophic death throes of a massive star, possesses a field of extraordinary potency. The magnetic energy stored within it is almost unimaginable, a kind of cosmic battery charged to its absolute limits. But from that moment of birth onward, it begins to surrender. The charged particles that swirl within and around the magnetar interact with that magnetic field, dissipating its energy in radiation, in X-rays, in gamma rays, in the light that eventually reaches Earth. Each burst, each pulse, each moment of activity represents a tiny loss. Multiply these moments across millennia, and the field weakens. The cooling happens gradually. There is no dramatic end, no sudden extinction. Instead, imagine a star that was once brilliant, that was once capable of sending gamma-ray eruptions across thousands of light-years of space, growing dimmer and quieter. After 10,000 years, its outbursts become less frequent. After 50,000 years, they are rare. After 1,000,000 years, the magnetar has transformed into something else entirely, perhaps into an ordinary neutron star, a pulsar still spinning and still emitting radiation, but from mechanisms far less dramatic than the wild magnetic storms of its youth. The magnetism that defined it has faded to ordinary levels. This fading is not speculative. Astronomers have observed it in the historical record of magnetar behavior. Some magnetars that were active and restless in the 1990s have grown noticeably quieter. Others show patterns that suggest they are indeed winding down, their flare activity declining across decades of observation. It is as if we are watching, in the most slow-motion way possible, the biography of a dying storm. What becomes of these sleeping former magnetars? The question sits at the frontier of understanding. A magnetar that has faded completely might be invisible to us, indistinguishable in many ways from a regular neutron star. It would still be there, still massive, still held together by the impossible density of neutron matter. Its core would still hold that superfluid realm, that strange inner ocean, but it would have surrendered its crown, the titanic magnetic field that made it special. Perhaps some of the quiet neutron stars we observe in our telescopes today were once fierce magnetars, now aged into obscurity. This cycle of birth, brilliance, and slow decline is woven into the fabric of what magnetars are. They are not permanent cosmic monuments. They are temporary. They are transient. Yet that transience does not diminish them. If anything, it deepens our sense of wonder. We are observing not eternities, but flickers, brief and extraordinary moments in the life of the universe. The fact that magnetars will fade, that their fields will eventually dissipate, that the greatest magnetic storms in the galaxy are destined to become whispers and then silence, this is not tragedy. It is simply the honest rhythm of existence, the pattern by which all things, even the most powerful, eventually yield to time. And there exists in the slow mathematics of stellar physics a profound connection between the violent death of a magnetar and the very substance of your body as you drift towards sleep. Everything heavier than helium, the iron in your blood, the calcium in your bones, the oxygen you are breathing into your lungs right now, was forged inside a star. Most of it came from ordinary stars that lived and died long before our sun even ignited. But some of the heaviest elements, the ones that make life itself possible in its fullest complexity, may have been born in the thermonuclear furnaces that still burn inside magnetars, or released in the cataclysmic moments of their transformation. Consider for a moment the iron that an ordinary star produces. Deep in its core, hydrogen fuses into helium, helium into carbon and oxygen, and gradually, over millions of years, the star builds heavier and heavier elements, layer upon layer, until at last it cannot push the nuclear reactions any further. The core collapses. The star explodes as a supernova, and the iron it created, tons and tons of it, scatters across the galaxy. This iron, ancient and recycled across billions of years, eventually condenses into planets and into you. You are, in the most literal sense, made of stardust that fell. But a magnetar's story is stranger and more intense. When a star so massive that it will become a magnetar reaches the end of its life, the pressures and temperatures in its core climb to almost unimaginable extremes. The intense magnetic field does something peculiar in those final moments. It can amplify nuclear processes. It can channel the energy of the collapse in ways that an ordinary star cannot. And in some models that physicists are still working to understand, the conditions inside a forming magnetar, in those microseconds when a massive core is collapsing down to perhaps 20 kilometers across, create an environment where elements even heavier than iron can be synthesized. Gold, silver, platinum, uranium, thorium, all the rarest and heaviest elements on the periodic table may owe their existence, at least in part, to these extraordinary stellar deaths. The Magnetar does not do this alone. Many of these heavy elements are thought to be produced primarily in the violent collision of two neutron stars, events called kilonovae that create neutron star mergers. And yet the extreme conditions inside a magnetar, the density, the temperature, the crushing force of gravity, combined with the most powerful magnetic field in the known universe, may contribute to this cosmic alchemy in ways that astronomers are only beginning to map out. The magnetar, in its own way, is a tiny foundry burning in the darkness, and the elements it creates or helps create do eventually escape into space, traveling outward in jets and winds and the diffusing remnants of ancient explosions. What is remarkable about this process is its slowness on human timescales and its inevitability on cosmic ones. A magnetar may have lived for only a few million years as a coherent, energetic object before it faded into obscurity. Yet during that time, or at the moment of its birth, it contributed to a process that would, across billions of years, lead to planets forming, and on at least one of those planets, to consciousness emerging. The gold in a wedding ring, the copper in an old coin, the silver in a mirror. Any of these might contain atoms that were forged in a magnetar explosion, or in a kilonova, or in the final moments of a massive star's collapse. The atoms that comprise your skin right now may have been part of that ancient furnace, and those atoms will outlast you, and will perhaps become part of other stars, other worlds, other living things in a cycle that has no beginning and no clear end. The mechanism by which these heavy elements are distributed into the galaxy is itself a process of both violence and grace. When a magnetar undergoes one of its great giant flares, it releases an enormous amount of energy. This energy accelerates material outward. It creates shock waves that can trigger the ejection of matter from the star's immediate vicinity. Some of this matter may be newly formed heavy elements. Some may be matter that was already present and is being pushed outward by the magnetic reconnection events happening in the magnetar's magnetosphere. Over time, as the magnetar fades, as its magnetic field gradually decays over tens of thousands of years, it releases less and less energy, but the process continues. The star becomes quieter, its influence on its surroundings diminishes, but the material it has seeded into space continues to drift, to cool, to eventually become part of interstellar clouds and nebulae. Have you ever wondered why some planets in our solar system have so much more heavy metal in their composition than others? Why Earth contains such abundance of iron and nickel and rare elements compared to Saturn, for instance? Some of this variation comes from the specific stellar populations that contributed material to our solar nebula billions of years ago. Some of it may reflect whether nearby supernovae or kilonovae or magnetar explosions happened at just the right moment to enrich the cloud of gas and dust that would become our home. In this way, the history of the magnetars in our cosmic neighborhood is written into the composition of the ground beneath you, into the metals and minerals that form the crust of the world. There is a quietness in contemplating this connection, a sense of deep time and deep space folding together into a present moment. The magnetar burned, it died, or slowly faded, its legacy scattered across parsecs. Atoms drifted in the void for millions of years, condensed in a solar nebula, became part of a planet, became part of life, and now they are part of your thoughts as you listen to this voice in the darkness. The magnetar will never know this. But in the cold mathematics of physics and chemistry, it is the architect of your existence, one among billions of such architects, each one contributing its small or grand share to the universe in which you have come to be. The heavy elements themselves, once created, are remarkably stable. They do not decay quickly. An atom of gold, created in a magnetar 10 billion years ago, is still gold today. This constancy is part of what makes the story so moving. The universe creates these elements once, burns them into existence in moments of extremity, and then preserves them forever. They travel, they mix, they become part of complex systems, but they endure. And in enduring, they carry with them the signature of their birth. Encoded in their atomic structure is the information about the conditions under which they were forged. Astronomers and physicists studying meteorites, studying the composition of distant galaxies, studying the remnants of ancient explosions, are slowly learning to read this signature. They are learning to identify which heavy elements came from which kinds of stellar events. And in doing so, they are slowly reconstructing the history of our own solar system, the chain of stellar deaths and rebirths that led to this moment, this place, this particular arrangement of atoms, temporarily organized into a conscious being, listening to a story about magnetars in the dark. The detection of magnetars represents one of the quieter triumphs in modern astronomy, a patient art of listening to the universe from observatories perched on mountains and launched into the silence of space. These objects, scattered through the galaxy in numbers we can only estimate, reveal themselves not through the naked eye or through simple telescopes pointed upward on clear nights, but through the patient watching of instruments sensitive to frequencies of light we cannot see. The X-rays and gamma rays that stream from magnetars pass right through the Earth's atmosphere, which means astronomers must place their most delicate sensors high above the world or beyond it entirely, into orbit, where nothing stands between them and the cosmos. When you think of detecting a magnetar, imagine not the bright flash of a distant lighthouse, but rather the faint tremor of a door slightly ajar in a dark hallway miles away. That is the sensitivity required. Ground-based observatories like those in the mountains of Chile or perched on the high plateaus of the southwestern United States host instruments that catch the echoes of these events, but the most direct glimpses come from space-based telescopes. The Chandra X-ray Observatory, launched in the late 1990s, became something like a dedicated ear turned toward magnetars, its mirrors shaped to focus X-rays that no ground-based instrument could gather. Hovering above the interference of Earth's magnetosphere, Chandra listens continuously, watching designated regions of the sky in patient vigil. The Swift satellite, launched in 2004, brought a different kind of attention to magnetar watching. Its name reflects its purpose, the ability to detect sudden gamma-ray bursts and pivot its gaze toward them within seconds, before the event fades. When a magnetar flares, as they do without warning, the sequence of alerts that flows between ground stations and orbiting instruments reads almost like a conversation. A burst detector registers the event. A message travels through networks. Within moments, telescopes on Earth and in space reorient themselves, hoping to catch the dying light of the outburst as it dims. This choreography happens in silence, in the small hours of morning when few people are watching the sky above them. The New Star Observatory, another orbiting instrument with a particular sensitivity to hard X-rays, has become crucial to the modern understanding of magnetars. Its design allows it to see the highest energy X-rays that magnetars sometimes emit, offering details about the violence occurring near their surfaces. When astronomers schedule observations of known magnetars, they are rarely observing sudden eruptions. Instead, they are tracking the slow baseline behavior of these objects between outbursts, watching for the gradual changes in their X-ray brightness that might hint at building tension within the star itself. This patient monitoring creates a kind of portrait, a timeline of each magnetar's personality, if you will. The role of human astronomers in this process remains essential, though it is a kind of work that unfolds quietly, often in the early hours before dawn. Teams of researchers maintain watch lists of known magnetars, coordinating observations across multiple instruments and sometimes across multiple observatories working in concert. When a magnetar suddenly becomes active after months of relative silence, it is often a human observer reviewing data, perhaps sipping cold coffee in a control room lit by screens, who first notices the change. They then make the decision to alert colleagues, to request urgent observation time from satellites, to begin the coordinated effort to capture as much information as possible about the event while it is still unfolding. Radio observations add another layer to magnetar detection, though magnetars are generally quiet at these wavelengths compared to their X-ray and gamma-ray brilliance. Yet occasionally, particularly active magnetars produce detectable radio pulses, and radio telescopes around the world contribute their own long-term records to the collective archive. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and other such facilities serve as part of a global network of listening posts, each contributing pieces of the puzzle when events warrant their attention. The archival work of astronomy, the cataloguing and recataloguing of observations, represents perhaps the quietest but most foundational aspect of magnetar study. Enormous data repositories hold years or decades of observations on individual magnetars, carefully labeled and preserved. When a new magnetar candidate is discovered, or when researchers ask new questions about known objects, they can reach backward in time through these archives, asking whether clues to understanding were always present in older data, waiting only for the right perspective or the right question to reveal their significance. This is the work of patient detective work rather than sudden discovery, the accumulation of quiet knowledge rather than moments of eureka. The future of magnetar detection is slowly expanding outward into new domains of observation. Some researchers propose that as gravitational wave technology continues to mature, these instruments might eventually detect the subtle ripples in space-time produced by magnetar activity or formation. This remains largely speculative, but it represents the way that astronomy constantly expands its sensory apparatus, finding new windows through which to see the same ancient objects. For now, the watching continues in observatories and control rooms, a steady, patient vigil maintained by people who understand that the universe reveals its secrets not through force, but through gentle, persistent attention. And yet, even with everything we have learned through decades of observation and calculation, magnetars remain wrapped in persistent riddles that astronomers still turn over in their minds during long observatory nights. We know they exist. We have watched them flare and fade. We understand much of what happens on their surfaces and within their cores. But the deeper question of how they come to be in the first place remains surprisingly open, still unfolding across the boundaries of our current knowledge. Consider the most fundamental mystery. Why do some neutron stars become magnetars while most do not? This is not a simple question, despite how it may sound. When a massive star collapses and its core compresses into a neutron star, something about that violent transformation must sometimes preserve or amplify the magnetic field to those staggering, unimaginable strengths. But the precise conditions that allow this to happen, the particular arrangement of stellar circumstances that tips the balance toward magnetar creation rather than an ordinary pulsar, remains genuinely unclear. Is it the rotation speed of the progenitor star before it exploded, the strength of its original magnetic field, the specific composition of its core material? Perhaps it is some combination of these factors, orchestrating themselves in ways we do not yet fully grasp. One possibility that researchers have explored with quiet fascination involves the idea of a dynamo mechanism, not unlike the process that generates Earth's magnetic field, but operating at the most extreme scales imaginable. In this view, the turbulent, superheated material in a newly formed neutron star's core might act like a vast cosmic generator, converting rotational energy into magnetic energy with astonishing efficiency. This would mean that the newborn Magnetar is not simply inheriting a strong field from its progenitor, but rather creating one, building that tremendous force from the chaos and motion of its own birth. If this picture holds truth, it would mean that magnetars represent a peculiar phase in neutron star evolution, a temporary state where this dynamo mechanism operates at peak intensity before gradually fading over millennia. But there is another strand of thought, equally plausible, that suggests magnetars might form through entirely different pathways depending on circumstances. Some theorists have wondered whether a merger between two neutron stars, or a close encounter between a neutron star and another stellar object, might in certain cases produce the conditions for a magnetar to ignite. The collision itself, the violent friction and compression, could potentially amplify an existing field to those extraordinary strengths. This would make magnetars not just the products of ordinary stellar death, but rare cosmic accidents, brief stellar configurations that arise only when the choreography of binary systems aligns in precisely the right way. There is also an intriguing possibility, still quite speculative, that relates to the internal structure we discussed earlier. Perhaps the formation of a magnetar depends critically on how quickly the superfluid core arranges itself, how its internal layers establish their patterns during those first frantic moments of neutron star birth. If the superfluid components settle into certain configurations more readily than others, they might naturally generate stronger magnetic fields. This would mean that magnetar formation is not so much about the star's properties before collapse, but about what happens in the first milliseconds after, about the physics of how matter reorganizes itself when squeezed to such impossible densities. In this view, every magnetar is a small miracle of internal architecture, a temporary flowering of magnetic power that will eventually fade as the star ages. There are also deeper questions about the relationship between magnetars and their stellar precursors that astronomers continue to ponder. Do magnetars preferentially form from certain types of massive stars? Do they emerge more readily from binary systems where stellar interaction stripped away the outer layers before the collapse occurred? Or from stars with particular compositions, rich in certain elements that might enhance or preserve magnetic fields through the transition to neutron star status? These questions remain largely unanswered because it is so difficult to trace a magnetar back to the specific star that created it. By the time we observe a magnetar, its progenitor has been obliterated, reduced to the infinitesimal remnant at the heart of the supernova aftermath. Some researchers have wondered whether the magnetic field structure within a magnetar might not be uniform at all, but rather patchwork and complex, with localized regions of vastly different field strength arranged across the surface and interior in ways we do not yet understand. If true, this would suggest that the formation process produces an intricate, almost organic pattern rather than a smooth, symmetrical configuration. We might imagine the magnetar's field as something more like a landscape, with mountain ranges and valleys of magnetic intensity, rather than a simple dipole stretching from pole to pole. And then there are the possibilities that lie even further from current mainstream thinking. Suggestions that magnetars might occasionally form through mechanisms entirely different from stellar core collapse. What if, in rare circumstances, a black hole accreting material at particular rates could somehow generate the conditions to birth a magnetar nearby? What if the collision between certain types of exotic matter at the edges of a neutron star merger could spontaneously produce that tremendous field strength? These ideas remain largely theoretical, sometimes even playfully speculative, but they remind us that the universe is larger and stranger than our current models encompass. What becomes clear, listening to these open questions, is that magnetars occupy a peculiar space in our astronomical understanding. We have learned enough to know they are real and knowable, to make genuine progress toward comprehending their natures. Yet we have not learned enough to tell the complete story of their origins. They invite further investigation, further patient observation, further refinement of our theories about what stellar collapse can produce, and what the universe permits matter to become under the most extreme conditions. In this way, Magnetars embody the ongoing dialogue between human curiosity and cosmic reality, a reminder that even in an age of powerful telescopes and precise calculations, the universe still holds genuine mysteries that we may spend decades approaching, slowly, carefully, piece by piece. And so, somewhere in the vast archipelago of the galaxy, Magnetars spin on in the darkness. These strange and solitary objects, born from the collapse of stars far more massive than our Sun, carry within them the memory of cosmic violence transformed into something almost meditative. A magnetar is, in many ways, what remains when the universe has done its work of extreme simplification, stripped away all the noise and complexity, leaving only the most essential forces at play: gravity, magnetism, the rhythm of a spinning core. The fact that we can know about them at all, across the incomprehensible distances that separate us, is itself worth savoring. That light and radiation, born in the moment of starquake or magnetic convulsion, travels for years through empty space to reach instruments built by patient human hands, instruments that listen, night after night, to the whisper of the cosmos. There is something deeply comforting in that continuity. The same atoms that once formed the core of a massive star, that felt the tremendous inward pull of gravity, that were compressed into something so dense that a teaspoon would weigh 1 billion tons, those same kinds of atoms are part of you, part of the earth beneath you, part of everything that breathes and grows and thinks. Magnetars remind us that death and transformation are not opposites in the universe, they are partners. When a star falls, something new emerges. The magnetic field that once seethed invisibly around a living sun becomes, in the magnetar, a force so concentrated that it bends the very laws of physics in ways we are still learning to understand. The X-rays and gamma rays that stream from a magnetar's surface are not destructive forces alone, they are signals. They are the voice of extreme matter speaking back to us across the darkness. In recent years, as we have learned more, the picture has become less certain in some ways and richer in others. We do not yet fully know how many magnetars exist, or whether they might play a role in phenomena we thought were caused by other objects entirely. The discovery of potential links to fast radio bursts, the hints that magnetars may evolve differently than we once imagined, the subtle questions about how they form, all of this reminds us that the universe still holds vast territories of mystery, and there is no urgency to resolve every question. Some of the deepest peace comes from sitting with what we do not know, from allowing wonder to exist without demanding answers. The magnetars themselves are patient. They age slowly. Over tens of thousands of years, their magnetic fields fade, inch by inch, and eventually they cool toward the temperature of the surrounding space. They become quieter, fainter, perhaps less alien, in some strange way, as they settle into a long sleep from which they will not wake. But even as one magnetar dims, others are likely being born. The stars continue their cycles. Somewhere, a massive sun is approaching the end of its life, having burned through its hydrogen and helium, having fused heavier elements in its core. Somewhere, gravity is gathering its tremendous strength for one final act of compression. And we, the observers, continue our patient work. We point our instruments skyward. We wait for signals. We listen to the universe tell its stories, night after night, season after season. There is something almost meditative in this practice. This simple act of paying attention to things that exist far beyond our touch, beyond our immediate understanding, it connects us to a very old human impulse, the desire to know where we come from, what the universe is made of, how it works. A magnetar, in the end, is not so much a mystery to be solved as an invitation to wonder. It is a reminder that extreme does not mean ugly or dead, that power and stillness can coexist, that the most violent events in the universe can produce objects of astonishing delicacy and subtlety, objects that spend their lives gently releasing the energy they were born with, slowly giving it back to the cosmos from which it came. In contemplating magnetars, we are contemplating something about the nature of transformation itself, the way that endings contain beginnings, the way that the simplest objects can speak the deepest truths. The dark is full of these spinning minds, these magnetic hearts beating their slow rhythm against the void. And we, for a moment in cosmic time, have learned to hear them. We have learned to listen. And in that listening, we touch something timeless, something that connects the matter of stars to the consciousness that perceives them. In the quiet of the night, as sleep approaches, perhaps that is enough. Perhaps that is everything.